Hello, my name is Marcelo Portugues Maurtua, and I will share the presentation entitled Using Machine Learning Techniques for Filling Missing Precipitation Series. This is a study that was carried out jointly with my colleagues Jose Luis Arumi, Octavio Lagos, and Alejandra Starr. Let me start with the location. The study considers three basins: Mala River Basin, Oma River Basins, and Cañete River Basin. They're located in the Lima region within the Peruvian territory, and they are part of the Pacific watershed. These are basins that are close to the Peruvian capital. Just to put this into context, there are studies that focus on water resources, hydrology, and we can see that precipitation is an important component in order to better understand the whole hydrological cycle. But before going into this, it is important to keep in mind that the Peruvian territory is composed of three watersheds: the Atlantic watershed, the Pacific watershed. We've got the Andes mountain range that divides these two watersheds, and we have the Titicaca watershed, where the waters drain towards the Titicaca Lake. So, as we have seen in the previous slide, that the basins are located here as part of the Pacific watersheds. So, the type of rainfall that takes place in this area is orographic rain. They are created in the Atlantic Ocean. They get to the top of the mountain range, and part of those clouds pass on towards the Pacific watershed, and that is what makes up for this great amount of rain that happens in this part of the Peruvian territory. The big problem that we have in every single basin is the following. One is that there is no homogeneity when it comes to the location of the different stations. Also, we find incomplete rainfall series, which is one limiting factor and very important when we want to carry out hydrological studies. But different studies have been carried out to try to fill this missing data, but most of these studies have been focusing for filling out monthly or yearly precipitation series, and there are very few research projects focusing on a daily scale. And this is understandable because there's a lot of complexity, and sometimes these precipitation series are very different between one station and the other. So the main objective that we're after with this study is precisely to fill the missing precipitation series but at a daily scale using machine learning techniques. So this was done using this methodological framework, which shows the different stages. We have four important stages here. We have the data collection, and this was done by using the database from the National Service for Meteorology and Hydrology in Peru. This is the URL, and you can have access to the stations through this link. The next process is the data exploratory analysis. We have two subphases. One is graphing the time series, box plots, and then is the analysis of the homogenization. And for this, we've used a library called Climatal that runs on the language R. And for the regionalization, we've also used R, but in this particular case is by creating our own codes so that we can use the k-means cluster method in order to create homogeneous regions. And one way of validating this is done through the regional vector technique. Now, for filling the missing data, we also then have two substages. We've got the machine learning models and optimized machine learning model. Each one of these stages use the same algorithms. The first one has multiple regression, then the k-nearest neighbor, then is the gradient boosting tree, and then random forest, and the same thing for the second substage. The only difference is that up here we work with default parameters, and here we work with optimized parameters. And all of this has been done through codes carried out in Python. So that's the methodology used. So let's look at some results. The first part is compiling the available information. So as we can see, these are the stations. Some of them are closer, are part of the basin or closer to the basin. This is the location. And we can see the data or the percentage of observed data and the percentage of missing data. So at a first glance, we can see that the station called Cañete, Bacaran, and Soxi are the stations that have the largest amount of missing data. So let's start with the data exploratory analysis, the time series graph, and then the box plot. Well, the box plot is always very important, and in this particular case, it was very important to learn the percentage of missing data, because that's precisely part of the issue that I need to solve. And for this, I need to know how much of it and how are they represented in terms of time. So here, Cañete is the one that has largest amount of missing data, and the one with the least amount of missing data is San Pedro de Pilas. And here we can see at a daily snapshot, this is Cañete. Light colors, this is the missing data, and what's dark or black is the data that exists. So another analysis using box plots, we can see here rainfall on a daily scale, and this is the monthly scale at the bottom. So we can clearly see that monthly there are a few outliers, and here also. So if we take a look at this, we might think that it all needs to be removed or deleted, but we have to be very careful. We have to see the date for these outliers and then to compare them, because sometimes it's a coincidence, or these could be values that have been taken in abnormal periods, whether it be El Niño or La Niña phenomenon. So if we continue with the data exploratory analysis, as mentioned before, we used a climate tool as the tool that is part of the R language, and it's really a process where first we analyze the data on a monthly scale. We learn where the breaks take place, and then we see if they actually, if those breakpoint outliers are really outliers or not. And then based on that identification, then we do the daily run, and we can start analyzing the results. So here we have a first result. We have the global statistic results for the homogenization analysis. So here we have the absolute maximum correlation, standard normal homogeneity test. Here we have root mean square, and here we have the percentage of original data. So all of this are equally important. But for example, here, when it comes to the homogeneity test, it's about 90 more or less. But here we've got an outlier. That's a leap, and that really calls our attention. Who's creating that? Because we have to keep in mind that this is global information. That means that all of the stations are clustered in there. So we can see that almost all the stations here have 93% of original data, but we have an outlier here, 55 of percentage of original data as the maximum value. So that's the global or compiled information. So if we break this down, we can look more specifically. So here we can see that the stations like Huancata, for example, have 100% of the data. That is to say, 100% of the original data. A large number of them have an important percentage, but here, Cañete, 55. Probably that's one of the ones that's pulling this down. And we can see some other ones, Soxy 67 and so on and so forth. We can see which ones have low figures here. So here the lowest ones are Soxy, Cañete, Pacaran. These are the stations that have the lowest percentage of original data. So once this process has been done, then we go on to the regionalization process, which are the stations that have a similar behavior. So for this, we can see that through clustering analysis in our language, as mentioned before, we can see the following clusters. This is a word dendrogram where we can see the way that they've been grouped. And if we look these on a table, these are the 4 clusters. Region 1 is made up of all of these stations, and so on and so forth. But here we can also look at it spatially, so we can clearly see how they have been represented. All of these stations within the different homogeneous clusters. Here, these are 3 groups. The group number 3, we have 3 stations in this group. These are the ones that have the largest percentage of missing information. And within the basin, it is the driest area. Then, with these clusters, then we can see that the machine learning technique is used. But for this, we also need to identify the target stations. Remember that some stations had 100% of the original data, but others had some data missing. So the idea is to start filling the missing data. So for cluster or region 1, these 4 have missing information, so they are the target station. And in this column, these are the stations that are called multiple predicting stations. Several stations that will serve as predictors so that we can fill the missing data for each of these stations. So with this, we have 3 regions because there's one region that I've left out because there is too much missing data in that one that we've left out. So here on this table now, we are talking about machine learning basically. So you can see that we have 2 groups. Here, these are the models, and these are 2 groups. We have the default parameters or the hyperparameters here on the right. This is for the optimized process of the model. So this is what's being used. Now we have to keep in mind that we've used codes that we have applied using Python. So the results, let me show you region 1 and region 2. So in region or cluster 1, we have Ayaviri, Huarochirí, San Lorenzo de Escomarca, and Langa. So the first one, Ayaviri, we have 2 groups. As you can see here, we have a statistical part for training, and the other ones are the same ones, but for testing. Remember, when we do machine learning, we have to take a number of samples, but we select some randomly for training purposes, and the rest for the test stage. So we can see the R-square, the root mean square error, Nash, p-bias, and so on and so forth. Test and for training. So the first one is for machine learning with default parameters. And for example, we can see that in terms of R, the one that has the largest one is a random forest. followed by the gradient boosting tree. That's for training. But when it comes to test, we can see that performance drops, and the ones that remains equal is the linear regression. But we can also see here the p-bias. Remember that that's an important statistical parameter because that tells us if the model or the predicted values are either over or underestimated. If it's zero, it's neither. But if it's a negative figure, then it's overestimating, and if it's positive, hold on, let me get this right. Negative overestimating and positive underestimating. All right. So this group here is precisely machine learning technique that optimize machine learning with optimized hyperparameters. So the one that provide the best results are both the gradient boosting trees and random forest, and they improve during the test. So we can look at the other statistics. For example, the p-bias, the one that gives the best result is the gradient boosting tree. It's neither over or underestimating, whereas here we are underestimating with the random forest. And that's how we can analyze for each one of the statistical figures, and we can see what's happening in each one of the stages. So obviously there's a lot of information, a lot of statistics, but I also want to show you a separate or different graph, which are the same results, but looked at through a graph that allows us to better understand. This is called the Taylor diagram, which shows a graph that has a correlation of with a standard deviation which is normalized. So this first graph is for the results for training, and this one's for the test stage. So in training, we can see that this one is one that's best performed, which is precisely machine learning random forest. That's the one that gives us the best results between 0.9 and 0.95, very close to 1. And on the test stage, remember that the first one was training and this one is stage, there are two models that have the best performance, which are the optimized machine learning gradient boosting tree and optimized machine learning random forest. These are the ones that give us the best results. And we can see something similar with another station. In this case, it's Warochiri. So it's a similar interpretation, as you can see. So that leads us then to our conclusions. We can conclude then that we can use the machine learning technique for these type of processes, which can interpret this variability of the precipitation in this area. Do not forget that when doing this, we use information, part of it for training purposes and another part for testing purposes. Depending the orography, it's 75% and 25% correspondingly. It is also important to do a good regionalization and homogenization analysis prior to actually using the model, because that's precisely where we need to fine-tune the quality of the data. So once all of that has been carried out, we can conclude then that the optimized machine learning, where both for the gradient boosting tree and for random forest, were the ones that gave the best statistical metrics. So they best interpreted the variation in the precipitation. So this is a technique then, or a methodology that can be used in future studies to fill missing precipitation series and data at a daily scale. So that's the presentation. I would like to close by acknowledging the Water Research Center for Agriculture and Mining and the Fontapa project for the support that we have received in order to carry out this work. Thank you so much, and I'm looking forward to your questions.